Hello, this is lecture 6, and in this lecture I'm going to talk about angular momentum, specifically angular momentum restricted around a fixed axis. Now, so far, pretty much all motion that we've considered, all rotational motion, has been around a fixed axis. So, for example, here I imagine two disks perhaps, and one of them is spinning, and I drop another one on top. What's going to be the result? And here I drew them as if kind of spinning around this rod of some kind, this axis that's physically stopping those disks from spinning in any other way. So the axis is straight, it's not this way, it's not that way, and that's not changing. This is different from free rotation, where an object is this pencil. It might rotate like this, it might rotate like this, it might spin in all sorts of ways in three-dimensional space. It's not just around a single axis. And we're going to come to that in the next lecture. So right now we're saying around a fixed axis, and maybe we should have said it about all the previous motion as well, all the previous rotational motion that we studied. But here we're going to make it explicit because angular momentum is the particular concept where it gets really, really interesting once you start thinking about it, not just spinning around a single axis like that. So I imagine I've got two objects, and they may or may not be spinning. They may be spinning at different rates. One may be at rest, one may be spinning, and I'm going to bring them into contact. So it's going to be an interaction. You can imagine if I have, if this one touches down on this one, there'll be friction between them. This one's spinning, this one is not. And what's the effect? Well, this one's going to start spinning because the friction drags it, whereas this one is going to slow down. Like this one will be dragged sort of forward at all points based on the friction with the other disk, as this one will experience a force the other way, slowing it down. So, in the case of a force of friction, the force would act essentially across the whole surface, but it would always create torque in the same direction. I hope that is fairly obvious. So, what do we know about the torque? Torque A on B. Right, so it's torque on disk B by disk A. Well, that is going to be equal to minus the torque by B on A. So why is that? Well, if you imagine, let's just simplify. Let's imagine instead of having the friction act everywhere on a disk, there are just a few fixed points where the friction acts. Well, for each of one of those points, I can apply Newton's third law that says the force that B acts on A at this point is the same that A acts on B at that point, except in the opposite direction. So this is really just applying Newton's third law to torque. And it follows from the fact that each force that contributes to the net torque on either one of the disks has a third law partner on the other disk. Now, what does this imply? Well, this is the torque on B, this is the torque on A. So this one is going to be equal to the moment of inertia of B times the angular acceleration of B, because this is the torque on B, just by A, but on B means it's affecting B according to Newton's second law of rotation. And then that's equal to minus the moment of inertia of A times the angular acceleration of A. Alright, so what is angular acceleration? Now, it's the time derivative of angular velocity. Now, in our case, the torque is going to stay constant if this is kinetic friction, right? The kinetic friction does not change, it just depends on the normal force between the two and the coefficient of friction, that all of that stays the same. So here I can just write this as delta omega B over delta T, where T is going to be the time of collision, do I mean by that? I mean by that the time it takes for those disks to essentially be in contact before they rotate together. It's going to be equal to minus the moment of inertia of A times the change of angular velocity of A with time. Why is a negative here? Well, one of them might be positive, one of them might be speeding up, the other one would be slowing down. And of course this is the same time, right? Newton's third law not only says it's the same force both ways, it also says that force acts for the same amount of time. Because otherwise Newton's third law would stop to hold if one of the forces is done after 5 seconds, the other one after 10 seconds. Just wouldn't make any sense. Okay, so now we've got this. Now we can of course cancel out delta t, right? Because the 1 over delta t, and then I can just take this to the other side. So I'm going to get I b delta omega b. So I've cancelled out the 1 over delta t. I'm going to take this over the side. IA delta omega a that is equal to 0. Alright, now I can expand this to change in the angular velocity as the final angular velocity minus the initial angular velocity. Let me do that. So I'm going to get I b omega b final minus I b omega b initial. Of course, initial final meaning just before, just after the collision. I don't care what happened earlier, I know what's happening half an hour from now. Plus I a omega a final minus I a omega a initial, that's equal to 0. We just rearrange this again. I'm going to take all the finals on one side, all the initials on the other side. So I'm going to get that I b omega bf plus I a omega af is equal to the same, but for the initial angular velocities. Omega a I. So this quantity, right, it looks like the total of this quantity, I omegas, those added up, is the same before and after. That's of course exactly the pattern that you know from translational mechanics, from linear mechanics, as being true of momentum, right? And if you derive momentum conservation, you start with Newton's third law, you apply Newton's second law on both sides, and you kind of proceed along the same way, except with forces and mass, rather than with torque and moment of inertia. So we're going to call this quantity the angular momentum. So our statement right here, in this case, for two objects interacting, two spinning objects that are free to spin around the same axis, like those two disks, like them interacting, is saying the total angular momentum is conserved. Right, that is essentially what this statement is saying for the particular system we looked at, or for any two objects that are interacting. Now let's write this down in define angular momentum properly. We haven't done it. I've said what it is, but let's actually write that down. Angular momentum give it a symbol L. Now I have to admit, I should have looked this up perhaps. I don't know where L comes from, how it came to be the letter L. But it's the general letter used for angular momentum, capital L, and that's equal to I times omega, and the statement is that that is conserved. Okay, now if we look back to the fact that torque torque tau is equal to I alpha, well, I can actually generalize it a little bit, alright? Like I alpha is d omega dt in general. Now, what I can do though is that what in a situation where I changes, what happens then? So really what I should be writing is that tau is dl dt. The same way CF compare with Konferatur, compare with that a force is equal to the rate of change of momentum. It could mean, usually it means that the velocity is changing assuming the mass stays constant, but it could also mean that the mass that's going at a particular velocity is changing. For example, if you imagine a sort of continuous collision, maybe wind blowing into a sail or water coming out of a fire hose, you can talk about the force with which you have to hold your fire hose. Well, you calculate by the rate of change of momentum, but not the velocity changes, but it's the amount of mass that's moving, the amount of water per second. So this kind of, you've seen that kind of example before. So torque is the rate of change of angular momentum with time. Okay, let's actually go back a step and actually do the calculation here for this particular example. I'm going to assume those two disks are identical. So angular momentum conservation example. And it's the example I've started with. I imagine two identical disks. See above. Right, I didn't specifically say they were identical. I'm just going to go with it now. So I have IA equals IB equals just one I. Right, so this equal sign just means call it I. I don't have to distinguish between the two, there's only one. Now if it is a solid disk, that might be equal to 1/2 times the mass times the radius squared, but I don't actually care about this right now. Then I get, before I have that IA goes 0, right? IA was not spinning at all, let's assume it's at rest, just dropping down. Whereas IB is spinning with some initial omega, some initial angular velocity, plus IB omega initial. I'm not going to use a subscript here because there's only one. And in the end, they spin together. So I'm going to get IA plus IB. Both get multiplied by the same omega final. Now those two are of course the same, it's all the same I, so you can straightforwardly see that this is just twice this, kind of what you expected probably, that the final angular velocity is just going to be 1/2 times the initial angular velocity, because this is 0, this is I, this is 2I, and so that's what you get. Very intuitive, very extremely simple example, but just an application of angular momentum. Let's do another example that's ever so slightly more interesting. So here it is. The example is the following. I imagine a blob of clay that I'm going to put on my spinning pottery wheel. Maybe not being very careful here, so I didn't drop it in the middle, and I didn't put it down before I started spinning. Anyway, it's a 1 kilogram lump of clay. I'm going to call this little m, mass m. And I'm going to imagine my wheel has a mass of 3 kilograms. I don't actually know if those are accurate values, 3 kilograms for a sort of pottery wheel, but let's just go with it. I imagine this is a radius of 0.4 meters. And I imagine I drop this lump of clay at distance 0.3 meters from the center, so about 3/4 of the way to the edge. Now, of course, this lump of clay, really, it's a lump, it has a size. I'm going to imagine it's small enough that it all is fairly close to the same point. So So I'm going to treat it like a point mass that's suddenly put down at this point here. And I imagine that my wheel spins at 2 rotations per second. So I want to figure out, well, once I just drop this lump of clay, right, that it comes with 0 angular momentum. It's not spinning initially, so it has to be dragged along by the wheel. Now again, it's going to be friction. I'm going to assume that this lump kind of sticks right away and does not really move across the plate, across the wheel, prior to coming to rest. It's a bit of an approximation, and you can calculate like what trajectory would actually follow if you drop it. It's a little bit more complicated, but for our purposes right now, we're going to assume you drop it and it stays in place. Okay, so let's figure out what the initial and final angular momentum is. Now, one thing I could do is I could actually work with F rather than omega, because if omega I is conserved, then Fi is also conserved, because F and omega are just related by 2 pi, right? If omega I is conserved, then 2 pi times omega I is conserved. But for our argument, for our example, I'm going to convert to omega just as a reminder of how to do that. So we have omega I, our initial angular velocity of the wheel, is 2 rotations per second, and that is of course 4 pi radians per second. This one has 0 omega. I'm going to take this to be obvious. I'm not going to write it down. I could write over here omega subscript lump of clay I equals 0. Now, to figure out the angular momentum, Li initially, it's going to be I disk times the initial omega plus I of the lump times 0, right, because it is not initially spinning. Let's write down what those values are. I disk, it's 1/2 mr squared. I'm going to assume this is a uniform disk, right? We derived earlier how we came to that result using essentially an integration of rings of different radius from the center to the outside. Practice, though, it's something you might just look up. So I'm going to get 1/2 mr squared times omega I plus, now what is the moment of inertia of a lump? Well, it's the lump around the center point, so that's just mr, but of course I'm multiplying it by 0, so I'm really just including this for completeness. So if you have a different example where it isn't 0, those steps still would make sense. Okay, let's plug in the values. I've got 1/2 times 3 kilograms, that's m, right, that's what we said for our example, times r squared, r is 0.4, so that is 0. Let me write it out, 0.4 squared, plus 0, 1/2 times 1.5, so times 3 is 1.5, times 0.16, right, 0.4 squared, comes to 0.24. Now what are the units? Well, this is in kilogram meters, for a kilogram meter squared, and then this is per second, so we end up with kilogram meters squared per second for the units of angular momentum. Okay, so I've got my initial value. Now what's in the end? That better be equal to the final angular momentum, the total, L final. That's going to be I disk plus I lump. They're now spinning together, so I'm just going to add their moment of inertia times the final oh, I made a mistake. I forgot, of course, then to include the 4 pi over here. No wonder I was just hesitating there. I was like, what's going on? No, here, mistake. Let's do it in red. Right. make a mistake. In here should include 4 pi. So that something looks funny here. I'm telling you nonsense, but I trusted my derivation there. Radians per, no, wait, what am I saying? Okay, 4 pi radians per second, right. Alright, so that goes in there. This was, of course, in meters. So I could have multiplied this by 4 pi. So what I'm going to do, so I'm going to take 0.24, multiply it by 4, that's 0.96, and I'm going to leave the pi in there. So I sort of anticipate that our final answer, we're going to go back to f, we're going to divide again by pi. Alright, sorry about the mistake, right? This should be in there, but the units are correct, because kilogram meter squared per second. So I included this correctly. I had not included the actual numerical value here. Alright, so that's equal to that. Now I can actually add those up, right? So what did we say? This one here is 1/2 mr squared. So 1/2 times 3 kilograms times 0.4 meters squared plus the mass of the lump of clay, which is 1 kilogram times its distance from the center of rotation, 0.3, so plus 1 kilogram times 0.3 meters squared times the final unknown omega f. So we can work out what that is in here. This I figured out was 0.24. That was the value I previously had there before I multiplied it by this. That is in kilogram meter squared. And I'm adding to this, well, 0.3 squared is 0.09 times 1 is 0.09 kilogram meter squared times omega f. Alright, we're almost there. That whole thing is, let's work it out. So I've got, that is 0.33 kilogram meter squared times my unknown omega f. But what is this all equal to? Well, we set up here, right, the final momentum is equal to the initial momentum, which is 0.96 pi. Kilogram meters squared per second. This was our initial momentum, angular momentum. Angular momentum. So that implies that the final angular velocity is 0.96 pi divided by 0.33. It's going to be in radians per second. So the kilogram meter squared, they cancel out, right, when I divide by 0.33. There's kilogram meter squared up here, kilogram meter squared down here. What is this? I'm going to be a little bit rough here. This is going to be essentially 3. It's only like 0.99 would be 3 pi, but pi is still included. So it's going to be, I want to go out on a limb here, because it's very close to 2.9 pi radians per second. Right? Very close to it. Alright, so what do I do now? Well, I wanted to find a final frequency of rotation. I've got the angular velocity, so I want to know how many rotations per second is that. Well, I just divide by 2 pi. So this divided by 2 pi comes to about 1.45 radians per second. And I do realize this is actually a small rounding error because I approximated it here to 2 significant figures. Now it's 3, but I didn't have a calculator. The method is what matters. And that's our final answer here. Alright, so in this case we had two objects interacting, and both those examples that we did, we had two objects interacting. Once it was two disks, once it was a lump of clay and a disk, and one of them was rotating, one of them was not. Now I want to consider a different situation now, where I have a single object and I'm going to change its internal structure in some way to change its moment of inertia. So now consider a single object, and I'm going to assume it's rotating. And I'm going to a single object whose moment of inertia is changing. So maybe you can think yourself of an example right now of what type of situation that might come up in. Well, I've got a demo for you, and that demo you can actually easily repeat at home. All you need is some kind of spinning chair or something like that. So here it is. For this experiment, I've seated myself on a spinning chair, so I can spin back and forth. This is just a stool, but you can do this at home just with any type of spinning desk chair or so. I've got two masses here, and they are each 8 pounds or 8 kilograms, I'm not even sure. Feels more like really just 8 pounds. So I'm going to use those to change my moment of inertia by moving them outwards. That increases my moment of inertia, moving them back in. Now, they weigh a lot less than I do, but when they're all the way out, they actually contribute significantly to my moment of inertia, because remember, moment of inertia goes with r squared. So being, say, 5 times as far out as my shoulder means the mass I'm holding contributes 25 times as much to the moment of inertia. The axis, of course, is vertical, and all the angular momentum here that you've got to think about just happens in the horizontal plane, right? There's no funny angles here. It's all spinning around an axis that points straight up. So I'm going to get myself spinning. I'm going to start a lot of moment of inertia out here, and I'm going to pull them in. You can see I'm spinning up, getting rather dizzy here. Oh no, what I'm going to do? I'm going to increase my moment of inertia again, and decrease my moment of inertia again. But because angular momentum is conserved, a bigger moment of inertia means a lower angular velocity, and vice versa. Try this at home. You can use any weights. The heavier, the better, of course, the more effective, but even just using your arms works. Give it a go if you can. A lot of fun. Also, really feeling dizzy now. So here's the example you just watched. Here I've seated myself on a spinning chair. I apparently always look a bit grim in videos when I take those, so this is an accurate representation of me, except with a haircut I could never actually pull off. So the masses, the values are all approximate, but I think that they're fairly good. So I have two masses. I'm going to imagine each one is 4 kilograms. And myself, I'm approximately a cylinder of mass 80 kilograms and maybe radius 0.2 meters, bit of an estimate. But I know it's not accurate, but it'll do, right? Actually, probably approximating a person as a cylinder for the purpose of a moment of inertia calculation isn't actually terrible. If you sort of look up and down yourself, that is the rough shape that humans have if you had to approximate them by a simple geometric shape. If you're a complicated geometric shape, well, then the moment of inertia calculation would accordingly be a lot more complicated, and we don't want to deal with that right now. Alright, so I am a cylinder of mass 80 kilograms, radius 20 centimeters, 0.2 meters. And when I was holding those masses far away from my body. I'm going to suppose they're about 1 meter away from the axis of rotation. Probably slightly less, actually. I don't think my arms are that long, but we're going to go with it. So R out means when the arms are out. That's what I mean by the subscript out. And R in, so when I was pulling the weights in, I was holding them close to my chest, then I'm going to assume they're also about 0.2 meters from the axis of rotation. Again, approximate values, as I say, my arms aren't quite that long, but it will work. It'll do for our calculation. It'll give us a fairly decent approximation. So when those arms are out like this, as shown in the picture, then I'm spinning at maybe approximately a quarter rotation per second. How quickly will I be spinning when I'm moving the masses inwards? That is the question. And of course, we're going to use angular momentum conservation here. So let's find my moment of inertia. So we need it twice. Once when the arms are out, once when the arms are in and the weights are held right by my chest. So I out is going to be a cylinder, and a solid cylinder is kind of like a disc, right? This is a cylinder, this is a disc. Well, this is a disc right here, but a cylinder is nothing but either a lot of discs stuck on top of each other, or maybe a really thick disc. In terms of angular momentum, in terms of moment of inertia, it doesn't make a difference as long as the axis goes like this. That's exactly the model I'm using for my own person. Alright, so I've got I, me, plus I of the weights. Alright, so let's work those out individually. I'm going to treat the weights as point masses. I'm a cylinder, or essentially a disc, elongated disc, 1/2 mr squared. Go with those values m and r. And I'm going to add to that the weights. They're essentially point masses, so it's going to be r out squared times m, except I've got 2 of them, so I'm going to multiply that by 2. Alright, so let's plug in the values. Let's see what we actually get. 1/2 times 40, so what am I doing, 80, jumping ahead here, kilograms, times 0.2 meters squared, plus R out we approximated as 1 meter, so that is 1.0 meters squared, times the mass was 4 kilograms of each weight, times 2, because there's 2 of them. And I know when I say weight, every time I hesitate, because weight, is a force, but also a weight is an object, right? Alright, let's work this out. 40 times 0.2 squared is 0.04, so 40 times 0.04 comes to 1.6 kilogram meter squared, plus 1.0 squared times 4 kilogram times 2, so that is 8 kilogram meter squared. So when I said in a demonstration, look, this fact that you square the R makes a huge difference, you can see why. Actually, those 2 masses together, even though they only add up to 1/10 of my mass, they have 5 times the moment of inertia that I have, because they're just so much further out. So that's, of course, that adds up to 9.6 kilogram meter squared. Now, what about the moment of inertia? Oops, you can't see this. There we go. What about the moment of inertia when the masses are held close to my chest, when I pull them in close to my chest? Well, everything is the same. Except we're going to use R in rather than R out up here. So what does that make? That is, the I haven't changed, right? This is the same. I'm still the same person. I am ignoring my arms. Of course, my arms actually changed my moment of inertia a bit too, but let's just pretend it's included in the effect of the masses. Or we just ignore it. It doesn't really matter. So I'm going to get 1.6 kilogram meters squared, but now I'm going to add to it not 1 meter squared, but 0.2 meters squared times 4 kilograms times 2. So this was the value here, R in instead of R out. So that's gonna come to, so this is 1/5 of this, 1/25 of it, unless I am mistaken. This together, I squeeze this down here, I'm just gonna do it, is 0.32 kilogram meter squared. So what does that add up to be? That is 1.92 kilogram meter squared. A huge difference. Huge difference. Alright, now if initially I was going 1/4 of a rotation, so let's convert that to an angular velocity. So F initial, F out, while my arms are out, was 1/4 rotation per second. It implies that my angular velocity while my arms are out are 2 pi times that, 2 pi F out, which of course comes to pi over 2 radians per second. Alright. So, now I want to apply angular momentum conservation. Angular momentum conservation. Right, there's no torque. There are internal torques. If you analyze it as a composite system of the masses and me reacting forces on each other, reacting torques on each other, but there's no external torque on the system as a whole, so therefore its angular momentum is conserved. Again, that logic is analogous to when you analyze a system in terms of normal momentum conservation. If you include all the objects that are included in any of the relevant interactions, there's no external interaction, no external force, then total momentum is going to be conserved. Same thing here. So we're going to use angular momentum conservation, and that says that I out times omega out is I in times omega in. Now we want to find this one here. How fast am I spinning when I'm pulling in the weights? So I'm going to get omega in is equal to I out over I in times omega out. And now I'm going to plug in values. Let's plug in the values we got. What do we have? This is 9.6. This is 1.92. The units are of course going to cancel out, times omega out, which we just calculated to be pi over 2 radians per second. Now these numbers work out kind of nicely. They just end up being 5, right? Because 9.6 times 2 is 19.2, so in other words this is 5 times 1.92. So I'm going to get 5 over 2 pi radians per second, essentially 5 times as fast, or I could write F in is not 1/4, but 5 times as much. Again, I could just work with the ratios of F and I just as well. 5/4 rotations per second. So it makes a huge difference, right? Those masses, as I said, they have a small mass compared to me, but a huge moment of inertia. mathematically speaking, because the r gets squared, so by pulling them in from here to here, from 1 meter to 0.2 meters, I'm going to get a factor of 5 squared, a factor of 25. Alright, of course those values weren't perfectly accurate, I didn't actually measure myself there, but they'll give you a fairly good idea of why I could see that effect so visibly. Now, why is this relevant? Where might this come up? If you ever gone figure skating, or even just watched other people figure skate, then you know when they skate and they spin and they pull their arms in or out, they can slow themselves down or spin themselves faster. Similarly, if you've got a gymnast who's doing some kind of jumping, spinning, something or other, landing on the mat, to stop, he or she may put out their arms to help slow down the rotation. Alright, so this was angular momentum along a fixed axis. That's fairly straightforward. And in the next video, we're going to take our whole rotational dynamics into 3D, where we might have changing axis of rotation. It's going to be more complicated, but I think it's also going to get a lot more interesting. I will see you there.